right, excellent. So hi everybody, welcome to our weekly check-in. Looks like we have almost everyone here. Sorry, I was a little scrambled. It's going to be my usual. I think it's going to be my weekly apology on every Wednesday when I get together and say, okay, here's what I tried to get done and I didn't quite get done yet. Because on top of getting the lectures ready for Tuesday, Thursdays, I'm also doing all the worksheets and everything for the 3150 labs. So this past weekend I was working hard on next week's lab, which starts tomorrow and Friday for the other sections. So we're kind of behind, but I have to stay ahead. So that's the good news, is we're all set for next week. But that means I was a little behind in getting stuff set up. So hopefully you saw the email I sent out a little bit earlier. If you check in Gradescope, there is now an assignment to turn in the oxidation lab. There is an assignment to turn in our next NMR homework, which will be due next week. I'll show you that today. There's a link for that up on the website. And what else? I have not yet graded your emergency kit labs, so those are in there still sitting, but I will get to those hopefully soon. And let's see, was there anything else? Oh, and the schedule, since we're here, we can go ahead and take a look at this. The schedule has been modified. When I started working on the handout for next week's lab, I decided that Beyond Labs experiment wasn't all too exciting. And it also didn't coincide very well with our 3150 calendar. So those of you who are taking 3150 right now, I want to try do the best I can to kind of have them match up. So I swapped it out. If you go to the schedule, you'll see that it's been replaced. But what we're doing here is here we have the Beyond Labs handouts, and one we're going to do next week is the hydride reduction, or carbonyl reduction using hydride. So it's nice because it's very similar to Grignard, and it's kind of the opposite of the oxidations that we started with. So I think it ties in very nicely. And I also have here the homework problem. There's a link here for the homework problem. We can go ahead and take a look at that. So you could download that from Gradescope, or you could download that from the website, which is where I'm at right now. And I also wanted to show you that there's a sample problem shown here, because this is kind of the level of work that I want you to show me. So up top in the instructions, it says that after you come up with the structure, you want to prove that you have the right structure. And so you want to go ahead and like we did in class, or like we did on Zoom, after you propose a structure, I want you to point with an arrow to every single proton and say, okay, here's what I predict it would look like. And do it just like this. Cover up the spectrum. Don't look at the spectrum. Don't use the numbers from the spectrum. Use the numbers from the table, right? So the table says, this should be peak A. The CH2 here should be a triplet, because it has two neighbors. Should be a 2 hydrogen signal, and it should be around 3.8. 3.8 is the number from the table. Okay, and then you can look at the actual. The actual is 3.65. So I don't want you to just take the information from the NMR and slap it down on top of your structure. I want you to predict what the spectrum should look like. And remember, that's our last step. That's when you confirm, yes, I have the correct answer, because everything matches up. Okay, and that's how I know that this is proton B and this is proton C, and so on. Okay, so I have that sample here for you to look at. I want you to list out your pieces. I want to see the progression of your work, of your problem solving. Check for degrees of unsaturation up here. I want you to mark up the IR spectrum with whatever relevant peaks you find there, and then that's that's all. Okay, so just wanted to put that out there so you know kind of what to expect and to know what I'm expecting. So there's an NMR homework, and the Grignard reaction is what we're doing for this upcoming week. And it is another Beyond Labs handout. So we're going to follow through follow the steps. There's actually going to be 3 separate trials you're going to run. And so you're going to be making observations for those. And we have our pre-lab assignment. So rather than doing, if you did not see your email that I just sent out earlier, rather than doing a synchronous quiz today, I just posted a quiz in Blackboard, and this one I'm going to let you take as many times as you want. So you could just keep taking it until you get whatever score you're happy with. And each time you take it, be sure to look at your attempt, because each question will have some feedback that will tell you more about the problem. So it's a nice way to kind of explore the experimental procedure a little bit, especially because we're not able to do it. And also the theory, and kind of think about Grignard reactions in a little more detail. The Grignard reaction is actually one of my favorites, so it pains me that we're not able to do it in person, because you literally throw the metal in there, you watch it dissolve as it reacts. It's phenomenal. And so I distinctly remember doing that as an undergraduate, and I always enjoy doing it when we teach it. So I do actually have in here an extension. Where is it? Down here. So there's an in real life extension. There's a couple of videos for you to watch. Very, very brief. You could speed it up if you want a little bit, and just so you could see what a Grignard reaction looks like when it's running. So so as usual, it has the worksheet to complete. And I'm not going to do anything specific to check that you had your pre-lab done for today. You could just turn that in with the rest of the assignment next Wednesday. So are there any questions about the Grignard assignment, that handout, just following through the steps, answering the question?
I have a question.
Go right ahead.
For the experimental results for part 1, number 5, does that belong in part 3? Because we haven't added the ether yet.
The mixture being analyzed. So the TLC, the reaction is in part 1. I'm sorry, we don't have we have the water solvent. Yes. So I may have kind of commingled that. That probably should have been down at the bottom. So you can kind of think of this as a standalone question, saying, if you have a mixture that's being analyzed that has the diethyl ether in it, then when you work it up, it assumes that you're adding ether. So if you're doing the TLC during the reaction, it won't be in there. But as soon as you drag over the SEP funnel, it's dragging over the SEP funnel and adding ether. That is kind of an assumed step that's not shown really well. So that would be part of any TLC that you're doing, would have that ether in there. But let's just assume we could just take this question on its own and assume that it has ether in there. But thank you for pointing that out. I'll rework the handout a little in the future so it's in the right place.
Okay, thank you.
Yeah. Any other questions if you've read through the handout? I also posted, where did I put it? Oh, I think it's in our Blackboard course. So when you go to the Blackboard course, I posted a link for a sample experimental procedure, because we're not writing the one up ourselves right now. And so you could kind of read through the different steps, and how do you make the Grignard, and then you use the Grignard, and then how do you work up the reaction. And so having a familiarity with the general procedure is going to be helpful for the quiz, because the quiz will have some questions about, well, what do you think this workup step is for? And what do you think this, why you're doing this? So, so we're going to try and have a little bit of a flavor of the real world experience with this, with some of the questions in your Blackboard quiz. And so some of them might not be obvious right away, but that's why I'm letting you take it as many times as you want, so that hopefully you'll learn something from the quiz rather than just having it be a standard assessment where you get a grade and then you move on. It's meant to be something that you kind of get some feedback from. Okay, any other questions? Questions about this? There's something in the chat, I think I missed it, about something on educator. Was it a question about NMR, or was it a question about, we went over this together, but is there a lecture on, do you mean on about the NMR? Because I had that posted earlier. Was that what the question was about? So I do
Yeah,
have
it was specifically in terms of checking our work, the last step of the process of when we do the NMR.
yes, you mean um, for like the kind of the NMR homework or the NMR that was related to the lab?
The homework.
Yeah, the homework. So I'm going to talk about this was the homework we had due last week, and we didn't have a standalone homework due this week. But there were some obviously some NMR questions in the lab report, and then now there's a new NMR problem set because now all of you should have gotten your graded work back for these problems 6 and 7. And so if you have any questions about that, I'm happy to discuss it, and I want to talk about it a little bit today for some to give you some general feedback too. But yeah, I do have lectures on NMR. Kind of part 1 is the introduction to NMR and how it works, and then part 2 is the nuts and bolts of how do you approach an NMR problem, and that's kind of what we did the first day this semester. So let's just take a quick look at these NMR problems. I don't have the key with me actually right now, but we can just kind of quickly go through some of the steps on how to put this together, right? Because I would be putting together my pieces, and the way we put together our pieces is right here. All we care about is this part. We look at the integration. So this tells me I have a CH3 and another CH3 and another CH3, and then I have a CH and a CH2. Now, some of you might have thought initially, hey, maybe that's an OH, and that's true. But take a look at this. What's the splitting pattern here? Do you see it's a quartet? It's not a singlet. OHs are almost always broad singlets. So if you see a 1 hydrogen signal and there's any splitting at all, doublet, triplet, quartet, whatever, that means that it's actually going to be a CH. Also, if you try to do an OH, you would find when you go to put things together, you don't have enough arms. You would never come up with a valid structure. So, so you want to make sure you are you step back and say, well, maybe it's a CH instead of an OH. We also have 3 oxygens. That's a lot. So that's kind of interesting. And we have an extra carbon because I only have 5 here, but there's 6 total. So when we come up with all our pieces, we actually end up with a couple oxygens. And I think that's now 3, 6. I think that's all the pieces here. Okay, now when we go to put them together, is when we look at the splitting patterns and the chemical shift. So if I take one of these CH3s, if I take this CH3 here, okay, and I decide what piece is it attached to, now is when I look at the chemical shift, and what do I see here? Look how far downfield all 3 of these are. They're all above 3. They're between 3 and 4. So what piece does that mean they are attached to? They are all attached to oxygen. That's the only thing that would bring them that far downfield. So my CH2 is attached to an oxygen. I have a CH2 attached to an oxygen. I have a CH that's attached to an oxygen. And I have a CH3 that's attached to an oxygen. Okay, and then we can look at the splitter pattern. This is a doublet. I have one CH3 that is a doublet, which means it must be attached to my CH. And I have another CH3 that is a triplet, which means it must be attached to a CH2. So I'm going through this much faster than I'm sure you would. Okay, but these, I've taken all these separate pieces all over the place and linked them together to be more logical pieces. Okay, and so now I have a carbonyl that has 2 arms. I have a carbon with 2 arms, and then I have 2 groups. I have a methoxy and an ethoxy that I can attach to the structure. Okay, and they can kind of, I gave full credit no matter how you assemble this, because there's a couple ways to assemble this. I don't have any C13 to tell me if I have maybe an ester or something else, but there's only one way to attach this with all the pieces working out, and that is making an ester here. Now the question is, can I decide? So let's build this up. So we have a CH3. Here's our two pieces. So we have a methoxy and an ethoxy, and we have to decide where to put them together. Now there is, and like I said, I gave credit whichever group you had here. So some of you had some different structures, and that was okay. Can I decide which one is attached to the carbonyl? I can actually, if I did some calculations, because notice that the methoxy group is way up here at 3.3, and the ethyl, the CH2, is way over here above 4. So it has very different groups attached to them. If we take a look at our tables for doing calculations, what you'll notice is that being attached to an ester oxygen is very different than being attached to just an ether oxygen. And so we can, this is going to have a much bigger shift downfield. So it's more consistent with saying that it's the ethyl group that is attached to the ester oxygen, and it is the methoxy group that is just attached to a regular oxygen. When we do those calculations, they're going to come out a little better. In other words, this oxygen is only shifting, what were the numbers, like 2.1 downfield, while this oxygen is shifting 2.8 downfield. So a little more advanced. There is actually a way that you could distinguish between these two, but like I said, I'm very happy with either solution. If you had these two groups exchanged, that would be totally fine. Any questions about the structure? Take a look at the feedback I gave. Now, of course, this is not the end of the problem. The end of the problem is I would have to assign each of these and label them A and B and C so that they match up. And like I said, what I would do is I would ignore the spectrum and just look at the structure. And so I would look at this. I would say, okay, this should be a 1 hydrogen signal. What is its splitting pattern going to be? Now I look, I see its neighbors. It has just 3 neighbors. So its splitting pattern is going to be a quartet. It's going to be a 1 hydrogen quartet. And what's its chemical shift going to be? Wow, that's not an easy thing to predict because it has actually 2 interesting groups attached. It has an oxygen and it's alpha to a carbonyl. So for that, I would actually have to calculate for a CH. I start at 1.5 and then I add the groups that are attached to it. It has an ether group and it has a carbonyl. That's an ester. So we're adding 1.1 and 2.1. So our delta is 1.5 plus 1.1 plus 2.1. So this is because it's next to a carbonyl, and this is because it's next to an oxygen. So what do we get? 1, 2, 3, 4, 4.5, 6, 7, 4.7 ppm. So in this is a rare case where I need to calculate rather than just estimate off of a table. Okay, and so down here I have a 3 hydrogen. This should be a 3 hydrogen singlet around 3.8 because it's just attached to an oxygen, and that's what I have on my table. Okay, and I do that for every single proton. Every single proton, predict the integration, the splitting pattern, the chemical shift using your tables. And then we look at the big picture again and we say, all right, does it match up? So over here, I said I should have a 1 hydrogen quartet around 4.7, and I have a 1 hydrogen quartet, and it came at 3.9. I overestimated here. So I could say my actual is 3.9. My calculation was a little off, but this is definitely proton B. It does match up. Do I have a 3 hydrogen singlet at 3.8? 3 hydrogen singlet at 3.8. I have a 3 hydrogen singlet at 3.3. There it is. That is C. And I could say my actual is 3.3. Okay, and so on. So make sure you're doing your work, you're showing your work how you came up with your structure, and then once you have your structure, show your work on to prove that you have the right answer. Questions about what's expected? And then of course we have C13 and IR on the homework too, so you can take a look at those. Okay, this problem was interesting because it has a one hydrogen signal at 8, which is like weird. That doesn't match any table at all. But we do know we have a degree of unsaturation, and the closest thing we have to a one hydrogen signal that would be close to 8 is an aldehyde. The number we have on our table is 9.7. But we do have a carbonyl. We do have a carbonyl. What can you tell me about proton B here? It's a CH2. And why is it so far down over 4? You tell me, why is it so far over 4? What must it be attached to?
Oxygen?
Must be attached to the oxygen. So this is actually our structure. This is actually our structure. And what I wanted to point out about this solution, again, going through the whole thing, predicting and confirming why this matches up. Okay, but what I wanted to point out is this molecule is interesting because it's not an ordinary aldehyde. It's actually an ester. It's actually an ester. And so this oxygen has resonance with the carbonyl, making this electron rich. So compared to an aldehyde carbonyl, this is significantly more electron rich. What happens when you become more electron rich? What happens to your chemical shift? You go further upfield. So that is why instead of being at 9.7, it was at 8. Again, not something I was expecting you to see or pick out or discuss, but I wanted to explain, why sometimes things aren't exactly where we're expecting them, and very often it's because of resonance effects. All righty. So questions about the homework? Please do check your homework. I added feedback here and there. I added feedback with the rubric when you made it like a common mistake. I don't know what that looks like when you view your results in Gradescope. So actually, if you want to like snap a picture of, hey, this is how I could see my score, and so I know where the feedback shows up. I don't want to write a whole bunch of feedback and have it never, be visible. Sometimes I think it shows up maybe as a little text box. So anyway, please do review your results, not just the score, but review your results so you could see how you did. And then that will get you ready for, oh, did I not bring it over? I didn't bring it over. The homework, I don't think I brought it over. I don't think I have it. No, that's okay. So just going back to the NMR that we have due next week. So you have a little more data. It's nice when you have an IR and a C13. That gives you some more clues about the structure. Okay, but the thing I wanted to point out, which I can't do because I don't have my pointer anymore, is reading the instructions. So at the top here, it says, show your work, assign all the relevant peaks, label each set of protons ABC. I already labeled them ABC for you. And then match them on the structure. And then here's our last sentence: to confirm your choice, predict the splitting patterns, and estimate and or calculate the chemical shifts. So do that last step where you're just, and don't make a table or anything fancy, just literally with an arrow, point to this proton and say, here's what I predict. And that's good news because that's when you know you have the right answer. All right, I think that's all I wanted to talk about today. I'm happy to stick around if you have any questions. I made the quiz available till tomorrow night, so because I didn't get it ready till today. So you could take it anytime today. You could take it as many times as you want. You could continue taking it tomorrow if tomorrow's better for you. But that will be our pre-lab quiz. And then you could do the Grignard experiment anytime today. I'm sorry, anytime this week up until next Wednesday. And then there's a little bit of pre-lab like there was for today. There's a short pre-lab for hydride doing a couple calculations, and that's due next Wednesday.
Hi, Dr. Starkey. I think I already saw my mistake when you were going over the NMR, but I went on Gradescope and I can't find the feedback.
So let's see. It's and that's what I don't know either. And so I don't know if the things that I type are just things that come back, you know, that I'm looking at as a grader, or if that gets shared, and that might be maybe it's an option that I have to turn on
Yeah.
to like share feedback. So thank you for that. I will go in. Yeah, it sucks to just like get this mystery grade, and I don't want to spend all this time. You know, what's nice about Gradescope is you don't have to write the same comment every time. But if you never see the comments, then that's not very useful. So
Yeah.
I'll go poke around in Gradescope and see if there's any options I can turn on. Thank you for that.
Perfect. Thank you.
You're welcome. Okay, so otherwise we're free to go. Like I said, I'll stick around if you guys have questions about your lab write-up, your oxidation report. You could turn that in anytime till midnight tonight.
Did you already grade all of the NMR homework? Because I'm looking at Gradescope right now and I don't even have, it's not graded.
Let me see. I think there were 20 out of 20 that were turned in. And so I can check on my end too.
Okay.
And then what I do is I post the grades. So I grade it in Gradescope, but when I'm done grading, then I sync it with Blackboard, and so the grade gets sent to Blackboard. So I don't know what you really see in Gradescope, and maybe you see it better in Blackboard.
Okay, yeah, I could check Blackboard.
Right, that might be a place to go. But I can
Right.
check. I'll check in Gradescope to see what it says about last week's homework.
I can share you my screen if you want.
Yeah, sure. Yeah, or you can send me a picture, either one. Yeah, it says that I've graded 100% of them, and it was all 20 students. So
You can see the grade on Blackboard, but it's not on Gradescope.
Yeah. You have to stop sharing your screen.
so you see it on Blackboard, right?
Yeah,
You see it on Blackboard as just a grade.
but there's no feedback.
And is it a link where you could click on it and open it, or
No.
it's just a number?
No. Yeah.
Okay. All right. And so let's see. So I'll look at this. I'll look at the settings for this assignment to see if there's a way for me to select many, show all rubric items, student visibility, show all rubric items, and show only applied rubric items. Okay, so I'll look into this and let you know if I find anything. But yeah, I'm definitely, you know, checking off which mistakes you had, and then not only do I have comments for each deduction, because again, common mistakes, but then for some of your homeworks, I added some feedback at the bottom, some global feedback. For example, you know, don't forget to include splitting patterns when you predict, you know, or that kind of thing. So it's very important that you're able to see that feedback at some point. So I know the feedback's there somewhere. We just have to make it visible. So export evaluations, download marked rubrics for each question. I don't know what that means. And let me see, is there a publish grades? All right, so I posted it. And then let me see if this is a second thing, publish grades. And maybe that was the button that was missing. So there's two things, post grade to Blackboard and publish grades. And those are two different things. I don't think I knew those were two different things.
I see your feedback remarks after I refreshed it.
That was it. Okay. So I have to publish the grades. That makes it viewable to you in Gradescope. And then when I click on post grades to Blackboard, that's when it does the syncing process. I think mystery solved. Thank you but now please do visit and go in and see if there's any comments with the with the rubric items.
Yeah, it's perfect now.
It shows
it
everything.
shows
Oh,
the
shoot.
points, and then it shows the comment. It's great.
Okay, awesome. That's the goal. And that's why, it's worth like me figuring this out and you guys figuring it out, because in the end, you're going to get a lot more feedback than you would otherwise. And it's a lot more efficient too. And it's very consistent, because I know I always will take exactly the same points off for the same mistakes, which I always try to do, but it's much harder to do without an automated system like this. So yay, we figured our first one out. All right. So when you submit the oxidation homework, if you use the the PDF of the homework assignment of the lab handout rather, then it recognizes, Gradescope recognizes that here's the area for question 1, here's the area for question 2. What I don't know what happens is if you have additional pages and that's part of your PDF, I think it just gets added to the end and I could just view them on my own, but I'm interested to see what that looks like. So this will be my first time using, like a PDF skeleton that you guys are uploading. So we'll see how this goes. We're exploring together. This is the semester of new technologies.
I had
Published-
another question
Yeah, go
about the
ahead.
lab.
Sure.
It was for part 1, the results with the water solvent.
Right.
And number 4, the TLC observation. For some reason, I'm not getting any results. It's the same, even after 5 minutes, and it says that it should only take 1 minute. Is it because water isn't a suitable solvent, so there's no reaction?
So do you get, well, no, there should be a reaction. And so that was one of the things that I discovered after I'd done the handout. I think you guys got the revised handout, is it actually matters the order in which you add your ingredients. So you have to add the Grignard and the aldehyde or whatever you're using first, and then add the solvent. So following the steps exactly in the exact order, because if you do it in a different order, that's when nothing happens. You're like, wait a second, that's not the results I was getting. So that might be, if you reset it and you make sure you follow the exact order, then that's when you should know, you'll see a change on the board. So, even without the TLC, you'll see that the initial ingredients that you had, the initial substrate and reagent, is now different. That's how you know that the reaction has taken place.
Yeah, I'm getting the 4 different components up on the board, but every time I do the TLC plate, for some reason it's not working. Because I tried doing it both ways. I tried doing the reagents first and then the water, or the water and then the reagents. Both times it was not working.
Can I give a comment on that? Because
Yes.
it happened to me.
Okay.
So sometimes when you grab the
The TLC
glassware,
plate?
Yeah, sometimes it's giving you the wrong one. So maybe if you take it first, that's the one that you need to throw it away, and another one that is remaining there is the one that you need to do. So you need to check it. You click on that, and then it's showing you which component it has it. And then if you put the TLC in the wrong one, it was not showing you anything. So that happened to me.
So you're saying maybe in the SEP funnel, it matters?
Mm-hmm.
Okay, yeah. So usually
depends on when you grab it. Sometimes you grab it in a different order, and then maybe it's the TLC that you're doing, it's the waste one, not the product. That happened to me.
For part 1, you don't separate anything.
For part 1, the reaction goes, let me see, I don't have my handout. I just have my worksheet here. Oh man, I just had it. And then it's gone. Let's take a look. There you go. I have my iPad. Let's go to the website. All right, where was I now? Just here. I have it right here. Alcohol oxidation. Nope, oh, there's the Grignard. You were already working on the Grignard, right? Okay.
Yeah.
Very good. So for part 1, we're going to collect the initial TLC as step 12.
Yep.
right? And then you start the reaction, and then you collect the final TLC, and you're saying you don't see any difference?
No, they look exactly the same.
Okay, so yeah, just I don't have the answer with me right off on what maybe is going different. Did you see a change in the board though? Did you see a
Yeah,
difference?
I
Okay,
did.
so maybe it's just not showing up on the TLC. I kind of thought it showed a difference, or maybe what it's just kind of showing is there's no product being formed. You know, it's still just showing the starting material.
Okay,
I'm
yeah,
sorry.
because I am
So
getting the
that's
4 components on the board,
so here we go. Let's step back. The TLC always shows the starting. There's two channels, right?
yeah.
So the one on the left is always your starting substrate. So that is the ketone or the aldehyde or whatever you're using there. And so if there's no reaction with the ketone or the aldehyde, then your reaction is still going to show the ketone or the aldehyde.
Yeah, because it ends with benzaldehyde. Like the reaction ends with it still in the
Exactly.
system.
Exactly.
Okay.
Mm-hmm.
That's because a Grignard reaction didn't happen. You didn't have a Grignard reagent attacking the carbonyl to make the desired product.
Okay, so should I just write that like next to the TLC plate?
Of yeah, what's in the you know, initial and what's in the final, and
Okay,
that's why. So that's why they
there's no
match.
change.
It's
Okay.
because the other stuff you're not observing, and so I'm sorry, but now coming back to this is it's again, I wrote this like 3 weeks ago and haven't looked at it since. So the other thing that is in there when the Grignard reagent gets quenched, you form, where is it here? You form ethane, but you don't see that on the TLC. You only see your ketone or aldehyde. So that's exactly what question 5 is asking, is why is that reasonable to not see that on the TLC? So that is what I think this is operating as designed. I think.
Okay.
All
Maybe
right.
that's why I was confused for 5 because I didn't understand what was happening in 4.
Right. Right. And
Okay.
overall, what's the whole reaction that's happening in part 1? Because the part 1 reaction is not the Grignard reaction that we were hoping to have.
Okay.
Yeah.
All right, thank you.
Good. You're welcome. Any other questions out there? You guys want to jump in? I know some of you tried to come to my office hours and I was in and out. I had my laptop here and I was working on a different machine. So if someone jumps into Zoom and doesn't like shout to say, hello, I'm here, I don't even know if someone's there. So I have to figure out a better way to get some kind of alert system on my Zoom to let me know when someone's entered the room. That would be nice.
I had a question about last week's lab, the
Yes.
oxidation lab.
Uh-huh.
So I'm having trouble with the NMR portion of it.
Okay.
Sorry,
Is that you dinging?
yeah, that's me. I just turned it off.
Okay.
Sorry about that.
No problem.
It's a group chat. So for the NMR portion for that, because it doesn't show us the integral or the integration.
It does actually.
Oh, it does.
There's a table on the bottom.
Is that the height? I thought that might have been it.
That's what the integration is. It shows it measures. It's not strictly the height. It's actually the area under the peaks, because you know, if you have a doublet or a quartet, it's kind of spread out. It's not just tall anymore. But yeah, the height is telling you the integration. So you'll see that those numbers are, you know, some numbers are twice the magnitude of other numbers. Some are 3 times the numbers. So that's what we translate to the 1H, 2H, 3H.
Okay. I'm gonna try that now.
Okay, so going back to the handouts we had when we did some NMRs together. What we had, nope, it was the practice ones. I didn't have any numerical ones, but we had some examples where it was drawn out graphically,
Mm-hmm.
right? So here's where we measured the height. And so what the table is giving you is it says like, okay, A has a height of 23 and B has a height of 28 and C has a height of, 45. And so you use those numbers to decide which one is 1H or 2H and 3H.
Okay, that's a lot more clear then.
Very good.
Okay, thank you so much.
You're welcome. Klein does a very nice job working with those numbers to come up with the integration. So you could refer to chapter 14. I don't know, 15. That's a guess, 14 or 15.
Okay.
One of those is NMR. And sorry, I missed you in office hours. I saw that. It sends an email when someone jumps into my office hours. I'm like, oh wait, you're gone.
Oh, no
Yeah.
problem.
So sorry, I missed you.
No
But like
problem.
I said, just next time when you jump in, just give a shout, and
Just
then
yell.
that way I'll know someone's there.
Gotcha.
Professor?
Yeah. Hi.
Hi, I have questions. So one of the questions is about page 10
Of which report?
that is due today.
Okay.
I was working on that, and I just want to make sure what I'm thinking is correct or not really. So when we have that benzyl ring with N on it and that with hydrochloric acid, I know that N is grabbing the H and Cl is leaving, and then I have the product of that. Now I know that NH needs to, yeah, there exactly. And NH is a very good leaving group, and we have Cl minus. After that, so is there where we need to stop or we need to go further?
No, this is simply a base reacting with an acid. So it is a proton transfer reaction. So it's just draw the curved arrows as you described, draw the curved arrows to show a proton transfer. So that's a mechanism, and then draw the products of that proton transfer. So it's simply a one-step reaction.
If you want to go further of that,
There's nothing else for it to do. So just like
we don't
if you
have enough information, right?
well, if you had hydroxide, reacting with H3O plus, or if you have HCl reacting with hydroxide, what is that product of that reaction? It neutralizes. The proton gets transferred, and now you have water and sodium chloride. You don't, there's nothing else that it could do.
I was thinking now NH group needs to leave.
No,
and
that
something
it's not
needs-
it's a base. What do bases do? They accept a proton. You're done.
Okay,
HCl is an acid. What do acids do? They donate a proton. You're done.
okay.
Yep.
Good.
Nothing else. Nothing else.
Okay, good.
Yep. You're definitely
Um,
overthinking it.
Yeah, okay, good. There was a question on the previous exam that, okay, we have this item, how we should know which phase this has, for example, in the room temperature. I was thinking about the melting and boiling point. What else can be the case? Because
No, that's pretty much it. Is melting point and boiling point determines its phase. It determines what it's going to be like at room temperature. You can also sometimes get a clue, like if you're looking at if you have a experimental procedure and it says, we need 3 milliliters of this reagent, right? Or if it says at the end of the reaction, we're going to recrystallize our product, you know, or we're going to distill our product, those you know, descriptions are telling you something about the phase of the compound, whether it's a liquid or a solid. But yeah, it's the melting point and the boiling point. I mean, it's the melting point, really. No, I'm sorry, it's both. It's both, right? A liquid at room temperature must have a boiling point that's higher than room temperature. That's why it's still a liquid, right? But it needs a melting point that's below room temperature, because now it's melted. It's not a solid anymore. Now it's melted. You see what I mean? So comparing what a melting point means below that temperature, it's a solid, and boiling point means above that temperature, it's a gas.
Okay, but I think I wrote this stuff, but I didn't get the full credit for the question. I was wondering what I did wrong then.
Did you, I mean, you could just send me a screenshot. In Gradescope, it might have a thing to ask for a regrade. If
It
that's an
was in
option, you could try
Blackboard.
submitting it that way, and I'll see what that looks like from my end. Or you could just take a screenshot and email it to me, or just, you know, send me an email and I'll take a look at it. But typically, if let's see, if someone said, what was the question? Is it
It was in the quiz last week.
it was a solid or a liquid? It was
I think it was solid. Yeah, I think it was solid, if I'm not wrong.
right. So I think with the solid, I think if the I don't remember exactly what I was looking for there. I don't have my thing with me, but if you just say like let's say you just say it has a high melting point. Okay, that alone doesn't tell me whether something is a solid or a liquid. Because a liquid could have a high melting point and a solid could have a high melting point, right? So you have to address both the boiling point and the melting point to explain what it is at 25 degrees. So that's, I know that was in some cases I didn't give, or they said, maybe they said, some students said, oh, it has a high boiling point, so it must be a liquid. Well, the solids have high boiling points too, right?
Yes.
Right? So so some answers were not complete that way.
Okay.
Yeah.
I'm trying to, but I don't know how I need to have a look to my answers. It's in Blackboard, so are they also on a Gradescope? Because I'm looking in.
That was a Blackboard quiz, right?
Yes.
Yes.
And I missed half point, and I'm not 100% sure, but I think I mentioned both boiling point and melting point.
And you don't see your response? You don't see your answer?
No, I can't see anything. I just see the grades and.
And when you click on it, you don't see your attempt? Is it a link? Okay, and Austin said it wasn't. Austin said you don't see it.
No, I don't
in
see anything.
Gradescope. I think that was some other time.
Me personally can't see much. Just that, the question and just the point I got. Just that, nothing more.
Okay, so that might be some Blackboard quiz settings that I can check as well about the tests. Let me see, full grade center. So anyway, just send it to me by email and I'll look into it, and then I can, I'll do two things. I'll check the settings of the quiz to make sure you guys can view your results, and I will take a look at your response.
Okay, because I can't send you anything because I think I just wrote it there, so I don't have any
Right,
proof.
so send me an email saying, please take a look at that question where I got a half point off, and then I will, I can open up your attempt.
Amazing, okay.
I can open up your attempt, but you should be able to open up your attempt too. You know, that's the whole point of taking a quiz, is you're supposed to get feedback from it. So.
I have more questions, but I will wait so other people ask first.
Okay, sure.
Hi, Professor. I actually do have a question.
Okay.
So for the failed experiment, I know that the flask broke. And is that because that it was due to high pressure from the gas? Since it
So,
didn't. I'm sorry.
well, no, I mean that sounds like a reasonable idea. And so what did you do? So where would high pressure come from?
It would be coming from the hold on, sorry. It would be coming either the benzyl alcohol or the aldehyde. Oh wait, no, it would be from the excuse me. It would be from the benzyl alcohol, right? Because we put in water and then we put in benzyl alcohol and
Right.
then we just put it onto the and then just put it onto the clamp. Or actually, give me 1 second. I think it's from the chromic acid, sulfuric acid, the oxidizing agent. Is that correct?
It's not about the specific components in there. It's just
Uh-huh.
what did you do? You added the ingredients, and then what
Right.
did you do? You put it on the clamp.
I put on the clamp and I
And
put
then?
on the heat condenser. And
Okay.
then so I started the reaction and then nothing happened.
And by starting the reaction, what do you mean? You
like turned on like the little knob.
right. Did you heat it?
I did, yes.
Okay, so what happens when you heat stuff?
Oh, it gets hot, like things get hot.
Right? You ever boil water?
Right, and it started boiling.
Right? So what happens when you boil water?
Oh, like there's like water like I wouldn't say, yeah, I would say gas or like gas in the form of like water starts
That's exactly what it is. When you're boiling water, right? That's all those bubbles coming up. That's water vapor. That's water vapor. That's water gas. That's the
right.
process of boiling, is taking something from a liquid state to a
Mhm.
gaseous state.
Mhm. Oh, I see.
So it's not at all a mystery where some pressure could have built up.
Oh, I see.
Because it'd be different if you just put stuff together and you kept it at room temperature and you just stirred away, then maybe that's
Right.
fine. But if you're heating something, that's when
Mhm.
we can't have a closed system.
And so nitrogen gas helps with that?
So it is a vent. We added a vent line.
That's what it was.
So
Okay.
it allows free exchange of nitrogen in and air out.
Oh, I
So it's
see.
a vent line that you put in.
That makes sense. Also have another question regarding with the HNMR. So for the benzoic acid, I used the method that you showed another student earlier, and for peak three, I got like, I'm sorry?
Your voice is cutting in and out a little bit. Are you talking about how to decide how many hydrogens there are for each?
Yeah, yes. Can you hear me?
Yes. So there's a table at the bottom. Did you use the table at the bottom?
Yes. And so I determined that for peak 3 that I got 2 hydrogen, and for peak 4 I got 3 hydrogens.
Okay, so I don't have the numbers in front of me,
Okay.
but we have 4 peaks. I mean, first of all, just look at draw out the structure of benzoic acid or benzaldehyde, whatever you're analyzing, right?
Okay.
Draw it out and think about what the NMR is going to look like. How many, kind of like we did earlier. It's like, how many unique hydrogens are there? How many hydrogens? There's 1 of this type. There's 2 of this type, right?
Right.
So thinking about what you're expecting. I mean, we're in a unique advantage because we have the spectrum and we have the structure. There's no unknown here. So all we have to do is match the 2 up, right? So you could use that structure and say, okay, I should have something here and I should have these aromatic ones, and this is how many there should be total. So you know how many protons you have total.
Right.
So your list under the number of hydrogens, that last column should add up to the number of hydrogens total in the structure.
Because I was like overthinking. I don't know, maybe if I'm overthinking it, because like my original answer, like I just put in like for the, I know for sure that peak 3 and 4 is a ring. Oh yeah, oh, no, 2, 3, and 4 is a ring.
Okay.
So that would mean that it would just have only one hydrogen, right?
Well, if a ring is symmetrical, right?
Right.
How many total aromatic protons are there in
Um,
benzaldehyde? How many total?
there's like 6, so it would be there would be
Okay, there's
3.
6 if it's benzene,
Uh-huh.
but as soon as you attach something,
Mm-hmm.
oh, you're saying there's 6 total. I'm saying how many are on the ring?
Oh, I'm sorry. Of like besides hydrogen?
How many hydrogens are attached to the ring?
Oh,
So we'd call
1,
those
2,
aromatic
3, 4,
protons.
5.
Okay. So that means if you think 2 and 3 and 4, let's say, are the aromatic protons,
Mm-hmm.
based on where they come in the spectrum, then
Mm-hmm.
there should be a total of 5 protons spread out over 2 and 3 and 4. You see what I'm
Right.
saying?
Mm-hmm.
So there might be 2 here and 3 here, or there might be 1 and 2 and 2, or there might be 1, 1, 1, 1, 1. I mean, it depends on how it
Oh.
shows up, but a total of 5 protons in that aromatic region are what we're expecting. So
Mm-hmm.
keep that in mind when you're trying to decipher those numbers and match them up and say, oh, this number is twice as big as this number. Well, that means if this is 1 proton, this must be 2 protons,
Oh, I see.
right? That's what we're doing with those numbers. The Klein textbook does a really good job he has lots of examples of using numerical values to translate those to 1H, 2H, 3H.
You wouldn't happen to know like the chapter or the page, would you?
So it's I think it's chapter 15. I think 14 is IR and chapter 15 is NMR. And but if you even just searched, if you have the vital source text and you just search for like integration, which is what you call it when you're trying to decide these numbers, you could find that.
Okay.
Because
All
yeah,
right.
the examples we did, I'm sorry about that. I should now that I know that the Beyond Labs uses those numbers,
Mm-hmm.
I'll be sure to go through some examples like that. But what we did in class is we just looked at the height. So we measured, and we never like measured in millimeters, right? But imagine if you took, do you see my A and B and C here on the
Mm-hmm.
screen? So
I
if you
do.
took A and B and C and you measured them, this is 5 millimeters, and this is or 50 millimeters, this is 53 millimeters, and this one is 72 millimeters,
Uh-huh.
right? Then how do you translate those numbers to
Right.
1 or 2 or 3?
Yeah,
So
that's
you're
what I was.
comparing, like, and a lot of times you kind of look at them and you can kind of see, oh, these 3 are all the same number, and this one is twice as those. So that's when you kind of say, oh, I think this is 1 and 1 and 1 and 2,
You're right. That's what I
right?
was having a difficult problem with, because like those lines on that example is really helpful to kind of decipher how many hydrogens, but unfortunately,
So there are no lines on the spectrum in Beyond Labs. There's a
right,
table underneath.
right.
Yeah, so use those numbers, and you can just sit down with a calculator. If you're not seeing the pattern, just take the smallest one and assume it's 1 hydrogen, and then divide everything by that number and see if you get all whole numbers,
Oh, okay.
right? And then if
Right.
you
All
don't,
right.
then you say, okay, well, the smallest number is actually 2 hydrogens.
Okay.
So then you cut that in half. You say, okay, so if it's 30, then 15 is what each 1 hydrogen is. So then you
Oh,
say,
okay.
oh, well, this one's 48. This must be 3 hydrogens, right? So
Mhm.
that's the process that you'll find in Klein and some examples that you can work on.
Got it. All
Yeah.
right. I'm
Does that
already
make
starting to see
sense?
it. Yeah, I'm already
Awesome.
starting to see it. Okay. Thank
Awesome.
you.
Awesome. You're welcome.
Oh, Dr. Starkey?
Yeah. Hi.
Going off of that. So typically in the examples that we've done in class, I've seen a lot of in the 7 to 8 region, we typically see the aromatics, right?
Typically right.
So if there's like a group around 7 and 8, is there ever a time when like an alcohol group is in between?
yeah, other things can come in that region, certainly.
So they don't have to be all clumped together. If something, let's say like a huge peak in between them, and I'm thinking that it's an alcohol, is that possible? Or do you know what I don't know if I'm explaining it clearly.
No, certainly. No, I think what you're saying, it makes sense. Yeah, sometimes you're going to have overlap of peaks. And so you say, okay, within this region, 5 of the protons in here, let's say, are aromatic, and this one little guy, I'm thinking maybe that's the phenol that I'm expecting, or the alcohol that I'm expecting.
Yeah.
And so, yeah, you definitely can have them overlapping and commingled.
Oh, okay. So they don't necessarily have to be all like clumped, all the like aromatics, all the protons that are associated with the aromatics, they don't have to be like necessarily adjacent to one another.
Well, and so even the example I have up on the screen, I mean, there's one that's at 7 and one's at 7.5, and those are hugely, different because this molecule has resonance. And so, you could easily, something else could show up in there. The thing is, usually the only things that are showing up in the region 7 to 8 are only the aromatic protons. So that's why I say just look at all the ones in that region and count them all as aromatic, and that's how you can figure out how many, what your benzene ring looks like. But
Okay.
but yes, it could be that sometimes, there's something else is in that area that's not an aromatic proton. It's not common, but that is a possibility.
Okay. Yeah, I tried doing I used a table, and then it's kind of like doing
Use the table
ratios
for what?
for the integration
Oh, right.
for benzoic acid. So it's like kind of doing like ratios, like dividing by like the smallest number.
Right.
Um, and then it just kind of completely ruined what I did before. So it just kind of like doesn't really make sense. I'm not sure.
Well,
I might.
again, take a step back and look at just the structure. Ignore the spectrum and look at the structure
Uh-huh.
and identify, the handout said, how many, it says there's 4 peaks in the NMR.
Yeah.
So can you look at the structure of benzaldehyde, and actually benzoic acid is the same. Each of these NMRs have 4 types of protons.
Right.
So looking just at the structure, can you see,
Yeah, I
the
could see
6
4
hydrogens? Do you see how they're grouped into 4 unique types?
Mm-hmm. So for like inductive effect has a play on if it's going to be upfield or downfield, right?
Sure.
So for that what is it? The side group, the carboxylic acid.
Mm-hmm.
How far does that inductive effect play, like down to?
Okay. Well, actually, so she's here a little. You see our little rat?
Yes.
Oh, she's so sweet. We had a little hairless rat. Sorry, I can't resist looking at her. We lost her last year.
Oh,
Okay.
no.
Sorry.
Sorry
All right.
for your loss.
What's that?
I'm sorry
Oh,
for your loss.
that's so sweet. Thank you.
I used to take care of rats, and they were so cute.
Aren't they just so lovable?
Yes, they're big, like puppy. They're just like puppies.
They're just so cool. Okay, I'm trying to add. I just made 4 copies of this. So with this, how do you add just a blank page? How do you add just a blank page? Oh my God, you're killing me. Let's add just a blank page. Sorry. Okay. And then, so rats are adorable, but the hairless rat, something about her, she cracked us up. Oh my God, she was so much fun. Okay. So, so we looked at 2 types. We've seen examples of 2 types of resonance with the benzene ring. And one is when you have an electron donating group, like an oxygen with a lone pair, that's actually going to add electrons into the ring. Okay,
Right.
so you might now, oxygen is inductively, pulls electrons out. So this carbon, we would expect maybe in the C13, we expect that carbon to be shifted downfield because it's attached to an oxygen. But when we look at the resonance effects, we see actually that the this carbon and this proton are actually very electron rich. Okay, so that's a resonance effect. Now, when you have a carbonyl, that's also a resonance effect rather than an inductive effect, because I can shift electrons around here. So this is an electron donating group. Are you taking 3150 right now, by the way?
Yeah. Mm-hmm.
Yeah, so we will, those who have had the luxury of already being finished with 3150 already know these terms, because this is stuff we're going to learn when we get into aromatic rings. We're going to do a ton of this resonance, and it's going to be much more, it's going to be very obvious to you when you see it, right? So in the meantime, though, I wanted to point it out to kind of explain why we could see such dramatic shifts in the NMR. And so now, because of this resonance effect, this proton is very electron deficient. So this one is going to have a high ppm. This one is maybe coming closer to 8, and this one is going to have a low ppm. Maybe this is one that's coming up closer to 7.
Right. Okay.
Okay. So, but actually, in these examples, you don't even have to worry about chemical shift at all. Just looking at the splitting pattern and the integration is going to make each proton distinct, each type of proton distinct, even just totally disregarding whether it's closer to 7 or closer to 8 or whatever it is.
Okay.
Okay, and again, it's coming back to, you know, predicting the spectrum. So this hydrogen here, what do you think about this hydrogen?
I
How
think
many hydrogens? Are there any other equivalent hydrogens?
yeah, the one opposite to that, like
Yeah,
two
because this
down
has
there.
symmetry, right?
That's what I thought. Well, I was kind of thinking for like, especially for like something like carboxylic acid between the two oxygens. I thought there was like a resonance effect happening there, which is acting like an electron withdrawing group. Is that correct? Is that okay to think like that?
Well,
Or,
both of these, the aldehyde and the carboxylic acid, both have the carbonyl, so they both have this same resonance.
uh-huh.
Okay, but again, getting away from chemical shifts, not thinking
Okay.
about chemical shifts at all. Tell me about this proton. How many, what's its integration going to be?
That one, I found it.
I mean, just looking at the structure right now, right? There's 2 of them, right? I mean,
Yeah.
because this isn't a molecule that we're doing in this lab. I'm just saying, analyzing structure and predicting spectra. So
Like
this hydrogen would be a 2 hydrogen signal, right?
right.
Because of symmetry, there's 2 equivalent protons contributing to that one peak.
Mm-hmm.
Okay, what would its splitting pattern be? How many neighbors does it have? Now for that, just look at one example of that proton and count up its neighbors.
Oh, only one. Oh, okay. I was thinking
Right.
like it has
Focus
like,
on one.
okay. It has 2 neighbors.
Mm-hmm. Making it
A single. No, sorry. A triplet.
n+1. N+1.
Triplet.
So this is going to be a 2 hydrogen triplet.
Oh, I see. I thought I was looking at both of them and then
When you're counting
the-
up neighbors, that gets complicated. Yeah. Yeah.
Oh,
So what you want to do there is just focus in on one and say, okay, for this, how many neighbors does it have? Now, it turns out that if you look at this one, you'll get the same answer because it's equivalent. So it also has 2 neighbors. But you just look at one of them to predict the splitting pattern.
oh, okay, that makes so yeah, that makes complete sense now. I thought there was gonna be
Okay.
like a quartet or something.
I know, right? That yeah, you don't want to add them all up. So just one at a time.
Gotcha. Okay, perfect. Thank you so much.
Awesome. You're welcome. We're getting better at NMR every week, I promise. That's the goal.
Can I ask a question just
Sure.
right here? I forgot to do the NMR through the lab, but I assume this like 1, 2, 3, 4 is just random, right? Or
They're numbered. They're numbered on the Bion Labs
okay.
numbers them and gives you the integration number
Oh,
for each of
okay.
them. And so I'm using the same. I want you to use the same numbers that they did. And so
Okay.
you label your spectrum. You label your structure. Oh, this is 1, and this is 2, and this is 3.
Okay.
to
Okay.
match the peaks in the NMR that are already labeled.
Okay, so okay, I need to redo that part. Okay, so I need to tell you then. I randomly I randomly numbered mine, and I would like to double check it with you. Do you think that's okay to do now or not really?
I want you to do the same steps that we did in our homework and the examples that we did in class and all that. I want you to look at the spectrum like we did, or look at the structure like we did
Yeah,
here, predict,
I did that.
okay?
So
And then if it matches what you see in the spectrum, then you have the right assignments, okay? But I want you to
okay,
change your numbers so that your 1, 2, 3, 4 match the 1, 2, 3, 4, because that's the only way I can grade it is if
you're right.
everyone thinks that
Okay,
the peak at 4.2 ppm, that's 1,
okay, amazing.
right?
Okay, so
And I
that's
think
the
I
missing
forget how
part.
it numbers it. If it, I don't know if it goes left to right or right to left, but it'll have the same numbering strategy every time you see a
Okay.
spectrum. So we'll get the hang of that.
And what we need to write down for the chemical shift? The number that they gave us
Right.
there, or
Right.
okay.
So you're translating the information from the spectrum into the table.
Okay.
Yeah.
Now I have a question. It's like not related to this. It's about the sig fig. Can I ask that?
Sure.
Okay, so it's about the pre-lab for today that we had. If I can't ask that question, that's fine. I know that
Sure.
it's because
No, that's fine because I didn't end up having a quiz based on that.
okay, good. So I just wanted I have some conversation with my friends and I'm now very confused. I would like to make sure I'm understanding the sig fig correct or not. So for
Right.
the first one, we like I started with 1.50 milliliter, right? So I assume that is the 3 sig fig,
Right.
and then I need to use the density and formula mass. So I'm assuming all of that we don't consider their sig fig. So I just
right. So when you use the formula weight or density, use it, all the numbers that you're given, okay? But knowing that you're going to end up with 3 sig figs at the end, you probably don't need your formula weight out to the thousandth place because that's not really relevant, right?
Okay.
So usually for formula weights, for molecular weights, we usually just go to the 10th place. That's plenty. Those numbers are insignificant because our formula weights are so big anyway. So you could go to the 10th place if you want for that, and then do your calculation, and at the end of it, just have 3 sig figs.
Okay, so that means so for sig fig, I put 0.0147. Is that correct?
So if 1, and 4, and 7 would be your 3 significant figures. Yeah.
Amazing. And the same for the second one, right? So I ended up at the end with 3 sig fig.
Right.
Okay.
And the thing is with for organic chemistry, to be totally honest, compared to Gen Chem, we don't care. I mean, I'll speak for myself. I really don't care about sig figs, but it's useful to kind of keep in mind on what is significant, because you'll see like students will calculate their theoretical yield or their actual yield. They'll say, okay, I was expecting 5 grams and I got 2.1 grams. So my actual yield was 62.587%. It's like, no, it isn't. Your actual yield is 62%. Everything beyond that is just, so I want to get you in the habit of not just taking everything you see on your calculator screen and vomiting it on the page and saying, oh, the more numbers I have, the better, right? You have to kind of just think about it and say, all right, all the numbers I'm dealing with have 3 sig figs, so that's probably what I'm looking for. And going that 4th and 5th and something, those are immaterial numbers. They have no meaning. So I want you to pay just a little bit attention to it, but I'm not going to go. It's not like Gen Chem where you're doing these calculations and it's, oh my gosh, you have to have exactly that, or it's you lose half the credit and so on. You will have classes that are quantitative. Organic chemistry is not a quantitative science. It's not a quantitative science, right? It's like, what was your yield? it was about 60%, right? That's not as good as 70%, but it's better than 50%, right? Where it's not, we're not about numbers for organic chemistry. It's about, can you purify your product? Can you analyze your product? Can you prove that that's the product you thought it was, right? It's very much qualitative science compared to some of the others, where it's all numbers.
Amazing. But
So
just,
I don't want you to freak out about it.
yeah, no, I just wanted for my
Yes.
knowledge to be 100% sure I'm
Yeah.
doing it correctly, or I
That
need to
sounds like
fix
you're on the right track.
But if we would have density with 2 sig fig, we wouldn't care about the density and we will still go with 3 sig fig, right?
Probably, because when you see something, a lot of times those numbers are very precise. And so, yeah, I would not cut down based on that. I would still try and keep the 3 sig figs, because that's where you're going to.
Amazing.
And I wouldn't cut out, like if you had a molar mass that was, 1,255 or some big number, I wouldn't cut that out saying, oh, that's not really its molar mass, right? Molar masses are precise numbers as well. So, so yeah, it's usually like going to the 10th place is a good practice when it comes to numbers, where grams and that kind of thing. Like, going to the tenths is plenty when you're measuring something out mass wise.
Amazing. Thank you so much.
Yes, you're welcome. It's probably a very vague answer that will not hold up in any other class that you take. But
Yeah,
that's kind of, you know what I'm saying though? It really is not a numbers class. It's
in
not a numbers
quantitative
class.
analysis,
Oh,
if we would miss just
exactly.
one, yeah,
Exactly.
we were losing a huge amount
Right.
of,
Right.
yeah.
But that's but look at the name of the class, right?
Yes.
It's quantitative analysis. It's
Yes.
literally all about the numbers. It's about the
Exactly.
numbers and the precision and the error analysis.
Exactly.
We have
Exactly.
none of that in organic chemistry.
Yeah.
So,
True.
you spill something on the bench, you kind of sweep it up and throw it back in. It's
Yeah, true.
our numbers are not that's not the point of doing organic chemistry.
Yeah, true. And for bonus, so that one is just if someone wish to do that, right?
Right. Optional.
Okay.
Yeah.
Good. Thank you.
All right. You're welcome.
Dr. Starkey, is the bonus like extra credit or?
It would be extra credit, little smidge of extra credit.
Okay, perfect.
Yes.
Thank you.
And the reason I included it is not just as busy work, but this is kind of a cool feature of Beyond Labs, is it lets you do that and see, hey, this is actually why I'm doing this step in the workup. And if I skipped it, this would be the problem that I encountered. So I think it's great because it actually reinforces this isn't just a laundry list of things that we're doing because it tells me to do it. It's like, no, every step in the workup has a specific purpose and function. And that's why it's important to kind of know what you're doing and why you're doing it. So I think it's a neat little side venture you could go on.
Yeah. Okay. Thank you. Got it.
Good. You're welcome.
And one more question.
Sure.
So for the Beyond Lab, I printed out my IR also. That's like just wasting paper, right? Because I don't think you need to see them, right?
Yeah, I included it in here because I had versions of it that Michelle Leslie had put together that actually had numbers on them. So those were nicer copies to use than what you're getting from the Beyond Labs. So yeah, I already included that in the report, so you don't need to include that printout.
So I don't give it to you, right?
Right. You won't need to do that. You can keep those.
Yeah, I think I just, yeah. Okay.
Yeah.
Thank you.
Excellent. You're welcome. Any other questions out there?
Just one question. So
Yeah.
you're going to post this video today? Because
I
I would
will,
like
yes.
to rewatch some of them.
Yes, certainly.
Great.
Yeah, that's what I was going to suggest, is I was going to wrap this up so it could start rendering that video.
Amazing. And one more time, that Wonder Woman in the back. Oh, that's awesome.
Isn't it
I
so
love
cool?
that.
So I have to, let's see. I have to,
so cool.
Let's see.
Maybe
Can
you can
guys-
post it
Oh
in
wait, no,
our.
wait. Here, hold on. I have to go back and share. Uh, continue. Stop broadcast, and I'm gonna share my camera.
That's so
Share
cool.
my. Share my. Uh-oh. Is it just my phone? No, it's my screen. Hold on.
You can have a picture of that and put it in Padlet.
Yeah, right?
Yes.
All right, so let's see. Oh, I know what I have to do. I have to go to my camera app. I'm like, how do iPads work? Hey, there it is.
Oh my God, that's so
Isn't that so cool? So they have all sorts of
Yes.
fan art at these Comic-Con type places. Mine, the one we went to was an anime expo. And this is not really just plain old fan art. This was a guy who actually worked for Marvel. And so I'm sorry, DC. Whoa, sorry. Don't freak out if I have any comic fans. So he worked for DC, so he actually had the art. So all that art is like official artwork from various comic books, and so he was commissioned to create this version for the movie, and it's we just fell in love with it. So yeah, we had to
So
keep
cool.
it up.
Thank you for sharing.
So yeah,
So
what I have to do
cool.
is I have to move it though, because I realize now with my camera behind me that it's hidden. I'll have to move it over to the right a
Yeah,
little bit.
would be nicer.
So anyway, something fun to have in the background.
Yes.
We'll be spending a lot of time in this room in the next couple months.
Thank you, Professor.
All right, bye-bye.
Bye.
Thanks, Dr. Sarkia.
You're welcome. You're very
Thank
welcome.
you.